All right, everybody, welcome to the video here for lesson number 8 on Newton's Law of Cooling. Newton's Law of Cooling is just a title for the lesson here. We're going to play with this this funky formula, but it just becomes an exponential / logarithmic question. So nothing really different here than what we did in lesson 7. We're just kind of extending it and doing some different types of questions here. So first opening exercise question asks us to explain why this equation represents exponential decay. So I'll give you a minute to try that. All right, and then we'll see if you come up with the same answer that I have. All right, so hopefully you tried this. So there's a couple ways we could have explained this. We could have said since the exponent is negative and the base is more than 1, we wind up having a decay model. We could say graphically, so when you graph this, it's going to have a graph that looks something like this. Or the best way to say it would be to figure out, well, what is e to the negative 0.248? If that number is between 0 and 1, it's decay. So in your calculator, if you do e to the negative 0.248, you wind up getting 0.78. 0.035 ... So since that's less than 1 and greater than 0, it's decay. So let's take a look at number 1. Number 1 gives us this graph of an exponential model. It talks about the temperature of a cup of tea when it's poured into a cup. And we can determine a lot of things about this cup of tea just by looking at this equation. So it says, based on the graph, what is the temperature of the tea when it's first poured in a cup? That's the initial temperature, so that's at time 0. So we'll say about 204 degrees Fahrenheit. That's the initial temperature. And it says, what temperature did tea approach as time increased? So as the time increases, your graph is slowly approaching this base value, right? So we have an asymptote line here at 68 degrees. We call this the ambient temperature. Essentially, it's the temperature of the room, right? If you take a hot cup of tea and put it down on a desk in your living room, it's going to eventually decrease in temperature until it gets to the temperature of the room. It's never going to get to be less than the temperature of the room because it's in that room. So it says, should we use a linear, exponential, or sinusoidal model? Right? Linear would decrease at a consistent rate, what this doesn't. Sinusoidal models would oscillate, so it would go up and down. So that would be the temperature goes down and then goes back up randomly and then back down. That doesn't work. So the only one that works here is exponential because it's gradually decreasing. All right, let's keep going here. So here's Newton's Law of Cooling. You've actually seen this before. We did it in the last unit as well. So one of the reasons why we have this in a couple different places for this course is it comes up on the Regents exam. They don't actually make you memorize this formula. They'll always give you this information, right? This is always going to be given to you. It's going to tell you what all the variables mean. So it gives us an equation, and it tells us essentially how much time it takes for a object to decrease to a certain temperature. So it says for a cup of tea in the previous problem, let's create a model for this function. So we know the ambient temperature, 68 degrees. We know the initial temperature is 204 degrees. So let's see what else we need to know here. So we could say T of T is equal to the ambient temperature plus the initial temperature minus the ambient temperature, e to the negative kt. We don't know k, we don't know t. However, we could simplify a couple things here. So if we do 204 minus 68, right, clean up that parenthesis, we can rewrite this as T of T is equal to 68 plus 136 e to the negative kt. We can't add the 68 and the 136 because the 136 is attached to this exponent. Now, For us to do anything, we have to first see that there's too many variables here, right? We have a temperature after time variable, we have a temperature variable, and we have a k, this constant variable. So let's find k. So to find k, I have to look back at my graph here for a minute. So looking at your graph, we want to find 2 points that are usable points. All right, so we have, let's see, if we follow my graph here, it looks like we have a good point at this point. So this point is 42.85. So this is a t value. This is a t of t value. Meaning if I plug those two numbers in, I should be able to solve for k. So if I plug in 85 for t of t, and we plug in 42 for t, using what we now know about logarithms, I can solve for k. So go ahead, try and solve for k, see what you get. Pause the video if you need to. All right, so hopefully you pause the video and you tried this on your own. So if we keep going here, we're going to subtract 68 from both sides. So I have 85 minus 68, gives me 17, 136, e to the negative 42k. I'm just going to put that the other way because it looks nicer. Divide by the 136. 17 divided by 136 is 0.125. That's a nice number. We'll use it. And since we have e, we want to take the natural log of both sides here. So natural log both sides. The negative 42k comes to the front. And we can keep going. So I have the ln, that looks weird. The ln of 0.125 is equal to negative 42k ln of e. We like ln of e because it just becomes 1. Divide both sides by negative 42. And now we know my k value. So when we find the k value here, we're going to round it out to 3 decimal places. That's probably what they would have asked us to do here if it was on the Regents exam. And we get 0.04951 ... We could actually round it a little bit differently. We'll just say 0.05 because that 5 will round the 9 up. So now we know the k constant, meaning I can come up with a generic equation that would represent any temperature at any amount of time by just putting back in the variables t and t of t. All right, let's keep going. Here's another question. So if we were in class, I'd say read through number 3 about this pot of tea and try and come up with the equation for the Newton's law of cooling here. So go ahead, pause the video, see if you come up with the right function here of the temperature of this mug after t amount of minutes. All right, so let's see how we did. So we know that we have a temperature as a function of time. The ambient temperature. So the ambient temperature is the outside temperature, so that's 18 degrees. Plus the initial temperature minus the ambient temperature, e to the negative k t. So if we keep going here, we can say the temperature as a function of time is equal to 18 plus 72 e to the negative kt. Now our job here is to figure out what k is. Luckily, we have more info. We have a time, and we have a temperature as a function of time. So if I plug those two numbers in, 65 for t of t, and 2 for t, we should be able to solve for k. So go ahead and see if you can solve for k. All right, so if you subtract 18 from both sides, so that's 65 minus 18, 47. Again, we'll just put the 2 in front. It looks better. Divide by 72. Not a nice decimal, so we'll leave it as a fraction, which doesn't even reduce. So we'll leave it as 47 over 72 equals e to the negative 2k. Again, we don't want to round that decimal, right? So if it doesn't come out to be a nice decimal that you can write as like 2 or 3 decimal places, just leave it as a fraction. Natural log both sides. Calculator's going to do all the work, so it doesn't matter. Toss that negative 2k up front. Ln of e becomes 1, and divide by negative 2. And we now know the k value. So if we type that into my calculator, ln of 47 divided by 72 divided by negative 2, we get a positive 0.213. Now, this wants us to write the function. So to write the function, I have to replace back in t of t. But now we're going to put in the k value we just found and leave t as my variable. There's your function. Now, it wants us to see if this function behaves how we think it's going to. So it says use technology, so we want to type this into our calculators. So let's go into our graphing calculator here. Go into y equals. So now that we're in y equals, we can plug in our formula. So we'll put in 18 plus 72 e to the negative 0.213 x. Now, before I actually even hit graph here, let's think. The initial value is 72, because that's the coefficient in front of the e here, right? We see the 72 is here. It's going to decrease until the ambient temperature of 18. So my window, if I use my regular 10 by 10 window, I'm not going to see anything. So if I just hit graph, I'm not going to see anything. So to change this window, the x values I'm going to start at 0, because time starts at 0. I don't know how much I'm going to go up by, so I'll leave it as 10 for now. I could always adjust it. My y minimum, I'm going to make 0. Even though the minimum value is 18, I'll just make it a little bit below. And my maximum number is 72, so I'll go a little bit above that. We'll go to 100, make it a nice even looking graph. So you can see it is a decay graph. It's going down over the course of time. You see it's starting to flatten out towards where about 18 would wind up being. So it behaves how it should. It says find the temperature at t equals 10. Well, to do this, I don't really have to do much math because it's going to be right in my graphing calculator. There's your value. At 10 minutes, it's 26.56 degrees. So we'll say t of 10 is equal to 26.6 degrees. We'll just round to nearest 10. We could have also plugged in 10 for t and solved it algebraically, but it didn't say to, so we'll just leave it as is. It then says use properties of exponents to write the percent rate of change. So to do that, I want to figure out what is this ratio going to come out to be here. All right, what is this multiplier? What is this number I'm going to keep multiplying? Kind of like what we did last chapter. So if I do e to the negative 0.213 in my calculator, so e to negative 0.213, I get 0.8082. About 4 decimal places is fine. So that means I can rewrite this function completely. I could say t of t is equal to 18 plus 72 times 0.8082 to the t. So I'm highlighting the fact that it's a decay function by figuring out, well, what is that base number going to be? I could even go one step further, even though it doesn't ask me. Actually, it does ask me, sorry. It says interpret the percent rate of change. All right, so I could say 1 minus r is equal to 0.8082. And I can solve for r. So if I have 0.8082, if I subtract 1 and then divide by negative 1, I get a rate of 0.1918, or about a 19.18% decrease. So it's going down about 19% every minute. All right, let's try another one. So here's a good example. Again, pause the video here. See if you can do this one by yourself. All right, so hopefully you pause the video. So it says a heated temperature of a pizza starts at 400 degrees. That's your initial temperature. And then it's placed in a room that's 75 degrees. That's the ambient temperature. It then says the temperature of the pizza is 150 after cooling for 4.5 minutes. All right, so that's your temperature after time. And 4.5, just write that over on the side, is your t value. So using all that given information, you can figure out the k value. So let's find the k value. So we could say the temperature is 150. The initial temperature, ambient temperature, we know. So the ambient temperature is 75 plus the initial temperature, 400, minus 75, e to the negative k times 4.5. Clean some stuff up. Move the 75. And again, I'm hoping you try this by yourself first. So you're just kind of going along with me and seeing if you got the same answer. Divide by 325. 75 divided by 325 is not a nice number, but it does reduce to 3 over 13, so we'll leave that. And then we can natural log both sides. Once I natural log both sides, that exponent can come to the front. So now I have the ln of 3 over 13 is equal to negative 4.5k ln of e, which becomes 1, divided by negative 4.5, and now I should know my k value. So we'll round that again, just nearest thousandth is fine. So we'll say the ln of 3 divided by 13 divided by negative 4.5, and we get 0.326. Now that k value is important because now that I know the k value, I can figure out a formula that would work for any temperature of pizza. So I could say the temperature of this pizza is equal to 75 plus 325 e to negative 0.326 t. That formula works for any amount of time. So hopefully you got this far on your own, okay? Now, the next part of the question says, at what time is the temperature of the pizza 120? So that's saying, all right, the temperature is 120. How long does it take? Let's solve it algebraically. We can definitely solve it graphically, but let's solve it algebraically. So go ahead, pause the video, see if you can figure out what t is. All right, so hopefully you do this. You subtract 75, get 45. And if you divide by 325, gives you a decimal, which comes out to be a fraction of 9/65. Again, don't freak out over the fractions. All right, so I'm just typing in my calculator 45/325. It's a decimal. I hit math enter, enter. It tells me the fraction it reduces to. So when you take the natural log of both sides, so we'll have the natural log of 9/65 is equal to, the exponent comes to the front, negative 0.326t ln of e. ln of e we like, it becomes 1. Divide both sides by negative 0.326 and figure out what that comes out to be in my calculator. So we'll do 9/65 divided by negative 0.326. And we get a time of 6.06 minutes. So we can see how we're kind of applying all of our skills together in one question here. All right, kind of tough, I know. Then says, what is the percent rate of difference between the temperature of the pizza and the room? All right, so what is the percent rate of change difference between the temperature of the pizza and the room? So percent rate of change. So percent rate of change, we want to make sure that we're going through and figuring out, well, what's the change in temperature? Temperature is uppercase T over the change in time. So the change in temperature, right? So the initial temperature was 400 and it went down to 150. And that started at 0. And that took 4.5 minutes. This is something you actually did in Algebra 1, rate of change. So if we go through and do some quick calculation there, 400 minus 150 divided by your negative 4.5, you get a negative 55.6, we'll round it, rate of change. Because the rate of change is negative, I know it's going to be a decay function, right? You might be saying, well, why didn't you do like e to the negative 0.326? Well, it's because it asked for a percent rate of change, all right? So we could even go through and go one step further here and say, what is that value of e to the negative 3.26? So if I do second e negative 0.326, I get 0.722, right? Which is really the same thing as 1 minus r. So if I subtract 1, I'm going to get about a 28% decrease per minute. That's an approximate because it's rounded. It's 27.8. So depending on how they ask the question is going to depend on what you want. Since it says rate of change, we want to do what I did here in blue. If it says to highlight the decay rate or the rate of decay, that's what I would do in red. That's what we did in yesterday's lesson. Hopefully this helped and we can move on to our homework lesson here. Again, remember, watch the video after you've done the homework assignment. That's the best way to do it. Also look out for a problem set coming so you can try those on your own. All right, hopefully I see you soon.